Hello everyone, I'm Cristina. I work for Hitachi at the European Research and Development Center as a researcher for industrial solutions. Today I'm going to present the content of the paper Rail Lone Worker Safety Solution with Deep Learning. This solution aims at improving the safety of lone workers in the rail infrastructure maintenance industry, using a smartwatch that monitors accident events and transmits the alert to the accident response team. This solution is a collaboration between Hitachi Rail and SNCF within the framework of SNCF's Rail Open Lab. And before going forward with the presentation, I would like to thank the other authors of the paper, Lan and Jung from Hitachi R&D, Frederic from Hitachi Rail, and Benoit from SNCF. The content of this presentation starts with an introduction, then an explanation of the methodology followed. Next, I will show to you a demo video of the solution, following with a presentation of the solution overview. I will go into more detail on the accident detection system part of the solution, and some final remarks. Let us start with the introduction. Here, I summarize the background that allowed for the development of this solution. There is an important law and regulations motivation for the development of this project. For example, the European Directive 89/391 sets as requirements that companies must provide adequate supervision and protection to workers' health and safety, especially in situations where the workers is alone at workstations. In addition, France, which is the country in which the solution was developed and implemented, applies a national work law that also includes lone workers. It states that a lone worker should be able to signal all distress situations and be assisted in the shortest delay possible. Also, safety solutions seems to be a growing market. According to research and market reports, the user-based lone worker safety solutions in Europe is estimated to grow at a 9.7% to reach 1.2 million users by 2025. It is in this context that Hitachi Rail has undertaken a proof of concept with French rail operator SNCF within the context of the Rail Open Lab to improve rail maintenance lone worker safety. SNCF's Rail Open Lab brings together industrial players with SNCF and RATP infrastructure experts, enabling digital projects and transforming the railway maintenance and operations practices. I will now explain the methodology used in this project. The first step of this project consisted on an on-site ethnographic study with interviews with workers and managers in order to understand the rail maintenance workers' work environment, the safety protocols already in place, and the elements which may cause safety risks. Also, the user's requirements. During this step, we learned that workers requested non-intrusive, low maintenance, and user-friendly solutions. It was followed by a solution ideation step. This includes the identification of all the potential safety risks, as well as potential solutions for those risks. During this time, we conducted multiple workshops with stakeholders in order to evaluate and decide on the final solution. Next was the design and prototype step. Considering all the inputs from the previous stages, the final solution agreed was a risk-based solution that at least would have to integrate on-edge artificial intelligence for automatic accident detection, SOS management rules over voice and data communications in order to notify all relevant agents of the accident event, and optimized battery consumption management functions. Once a stable prototype was developed, there was lab testing and then on-site testing, with continuous feedback for further tailoring to the rail maintenance work idiosyncrasies. Up to today, we continue collecting feedback from workers and adapting the solution to their needs. I will now show you the demo video of this solution. The audio is in French, but the subtitles are in English.
On est venu tester un système de protection des travailleurs isolés. Le travailleur isolé, c'est un sujet qui est très important pour la SNCF parce que beaucoup de personnes sont amenées à travailler seules, rénover, entretenir les voies et il faut être capable d'intervenir rapidement en cas de problématique, d'urgence pour secourir la personne.
C'est très simple, hein. L'agent a juste à mettre la montre à son poignet. Elle va être connectée au portable de l'agent. Elle va détecter de façon automatique la chute ou l'immobilité. Et si jamais elle souhaite faire un appel, qu'elle n'a pas son portable à proximité, il y a une possibilité de faire un appel au secours manuel. L'avantage de cette montre, c'est qu'elle est géolocalisée, juste quand l'alerte est déclenchée. Donc pour pouvoir justement aider les secours à retrouver la personne sur les lieux de travail. L'idée à terme, c'est de déployer ça à l'ensemble des agents qui sont sur le terrain et qui sont travailleurs isolés.
Tout est fait pour simplifier à outrance, je vais dire, le modèle et ne jamais rentrer par un ensemble de paramétrages qui peuvent être fastidieux et compliqués à gérer à court et moyen terme.
Hitachi est venu à un rendez-vous, on est allé voir un agent sur le terrain pour qu'il visualise vraiment donc, les problématiques, les dangers qu'il peut avoir, enfin l'environnement de travail en fait, de l'agent pour pouvoir nous proposer plusieurs solutions qu'on a adaptées.
Dans le cadre du RAID Open Lab, on a la chance de pouvoir avoir accès à des gens qui vivent au quotidien les tâches et à partir de là, qui sont capables de nous exprimer les problématiques qu'ils ont, qui vivent au quotidien et on peut les interroger, on peut explorer avec eux ce qui peut faire sens ou pas.
En fait, l'importance de travailler avec les entreprises externes comme Hitachi, c'est qu'ils nous apportent leur expertise en matière de technologie qu'on n'a pas forcément.
Ça permet également d'avoir accès à un ensemble de PME, start-up qui travaillent au niveau de ce milieu et comprendre comment leur technologie peut faire sens au niveau du milieu ferroviaire et imaginer avec eux des solutions système d'envergure.
Let's now cover the solution overview. This solution targets the process of detecting, communicating, and managing accident events. For that purpose, it uses a smartwatch that detects and triggers the alerts, and it is supported by a smartphone that communicates with the smartwatch and sends the alerts to the accident response team. Regarding the technical overview, the smartwatch is running a JavaScript app, and the AI model that triggers automatic events is developed in TensorFlow and compressed into TensorFlow Lite. The main features that we find in the smartwatch are the rule-based SOS triggering, that this function has also several subcomponents, such as the automatic triggering based on the combination of the AI model and workers' parameter settings, such as analytics on the driving behavior and the machinery operation. That is going to improve the accuracy of the model. It also includes the possibility of manual SOS triggering by pressing during a certain amount of time one of the buttons of the smartwatch, and the option of canceling alerts in case of false positives. There are also battery life optimization functions, including GPS activation management, lack of communication or white zone protocol, let screen activation management, etc. All these are critical components for the battery consumption. Next, it's also important to mention the HMI design. A user-friendly design was one of the main requirements by the workers. It has been particularly designed for the rail maintenance industry, for example, by including the white zone alerts, that is, alerts in areas that there is no cellular network. Also, privacy protection, sector-based communications, etc. And as I mentioned previously, the smartwatch connects to the smartphone. It uses Bluetooth Low Energy. And for the information exchange, the team designed standardized messages that are common for all the steps of data transmission. Then, on the smartphone, we have an Android-based application that includes functions such as communicating with the smartwatch using Bluetooth and with the accident response team using cellular network. The phone uses voice communication in case of accident and transmission of the event-driven standardized messages sent by the smartwatch if an SOS alert is detected. These messages are going to contain relevant information for identifying the device that emitted the alert and locating the worker in order to minimize the response time. I'm going to explain next one of the most important functions of the solution, the accident detection system that runs on the smartwatch. This is a subcomponent of the detection system, being the other subcomponents a lack of movement function and a manual triggering function. And the detection system is the initial step that triggers the communication and management of the accident events. This solution has two ways of initiating the accident triggering, either automatic or manual. The automatic detection can be either activated by a human activity recognition model or by a lack of movement detection function that runs in parallel. On the other hand, the manual triggering occurs when the worker presses the SOS button in the watch during a predefined time duration. Some extra details on the human activity recognition models. The models uses convolutional neural networks for classifying events into two classes, either activities of daily life or ADL, which is a category that merges all activities that are considered normal, or accident class, which includes events with lack of verticality under specific conditions. The model takes as input 3 coordinates time series acceleration data. For the training, we used a combination of a publicly available watch dataset, the UMA-FALL dataset that includes ADLs and fall data, and additional data generated internally by the team using the same wearable device in which the model would be installed. The generated data sums up to approximately 10,000 points and includes sector-related activities and additional accident data. the final proportion was approximately 80 to 20% for ADL and accident data, respectively. It is relevant to mention some important constraints that we encountered during the development of the solution. And the main one is the limitation in the resources available in the smartwatch. This was overcome by making trade-offs in the model and data input size. Regarding the model size, the hardware resources made us keep the model size below 3,800 bytes after compressing the model in TensorFlow Lite. One of the decisions that reduced the model size by the greatest amount was to group all ADL's activities in one class, even though that implies a loss of information in the predictions. It doesn't compromise the model objective of detecting accidents. The next trade-off is regarding the input data time window. That is, the number of seconds of time series data that is going to be the input for the model. On the one hand, bigger time windows are better at detecting longer tasks. But on the other hand, smaller time windows are better at identifying shorter tasks and task transitions. That is rather the case for the accident detection case. Finally, the trade-offs in input data frequency. Greater frequencies is going to imply more data values, which generally translates into a higher accuracy, but equally into heavier models and more storage needed for both the model and the data. In addition, with limited resources, it can translate into execution time errors. That is, when the resources don't have enough time to run one execution cycle before it has to start the next one. Therefore, considering both requirements and limitations, the model finally runs at a frequency of 4 Hz. It has an input size of 3 seconds with a model execution of 2 seconds. That implies data overlapping in executions, but that is going to be good for increasing the accident detection capabilities. And the overview of the accuracy. When the AI model runs by itself, its accuracy is around 93%. This is mainly due to the fact that in the rail maintenance work, there are multiple ADLs that have high impact. This is why we implemented additional rail-based function consisting in movements analytics. This is mainly reducing false positives. And like that, we bring the accuracy up to approximately 98%. And the false negatives are going to be captured by a lack of movement function that runs in parallel, although with the delay of the lack of movement duration. And with this, we have covered now the most important aspects. I would like to finish with some final remarks for the entire process. We highlight the ethnographic research as a useful tool for understanding the environment and the sector-based user needs and requirements. The importance of co-creation for enabling direct discussions with end users and direct feedback about solution design and testing since an early phase. Also, the inclusion of multiple stakeholders, such as workers, the safety management team, the accident response team, etc., made necessary the event-driven communications using standardized messages for everyone to have clear and organized information of all the events happening. For reducing the response time, we also include event description information such as GPS location, SOS triggering mode, etc., enabling the accident response team to properly manage the accident actions. Finally, recall that the reliability of accident detection is key. That is why we combine AI detection with the rule-based analytics functions for sector-related movements, and the false negatives are captured, but with a delay, by the lack of movement function that runs in parallel. And we have arrived at the end of the presentation. Thank you for making it to the end, and I will now be happy to answer your questions.